All right, let's learn a quick and easy example related to closed balanced energy balances in a system. So, this is a very typical type of problem that we would see in thermodynamics or in chemical engineering where we have piston cylinders. It's a very traditional type of problem. So basically, what we're doing is we're putting gas inside of a cylinder and we've added this movable piston that can go up and down. We know some information about the initial temperature, and then we place that in the boiling water, and the piston stays in a fixed position. We're going to heat and transfer some heat to the gas, and we're going to see a change in temperature and a change in pressure. The piston is then going to be released, and the gas is going to do a certain amount of work, moving the piston to a new position. And we know the final temperature is going to be 100. We're looking for the energy balance of each of the two stages. In each case, we want to know the unknown energy term in the equation. So when we solve the problem, we're going to consider the gas to be the system. So this is going to be something that's important for energy balance problems. We need to know what we're defining as the system. So this problem gives you the definition of what the system is, and that's good. And then the other piece of information that you get here is that we want to neglect the change in potential energy of the gas as the piston moves vertically and assume the gas behaves ideally. So we don't necessarily have a flow diagram to draw here, but it might be nice to draw ourselves a diagram. So the first thing that we might want to do here is we might want to draw ourselves a little diagram. So remember, you can pause the video at any point if you want to write this down and then just listen, whatever works the best for you. We're going to start with here's my little piston that I drew right here, and here's my little stopper. This thing is keeping it in place. And initially, this cylinder has gas inside of it, and it's 25 degrees Celsius. The first phase, I'm going to move my paper down just a touch. The first phase is to heat it by adding heat. So from here to here, we add 2 kilocalories of heat. And that's going to change the gas to 100 degrees Celsius, but we kept that stopper in place so that that piston doesn't move. Then the second phase is that we're going to do work on this. And that work is actually going to be negative in this instant because the gas is doing work on the piston itself. So it's moving from the gas to the piston. So we're going to define that as negative in this class. And it's going to stay at 100 degrees Celsius, but we're going to see that that piston rises. And even though it rises, remember that the problem says we can neglect the change in potential energy as it moves vertically. So there's two phases that are happening here. There's one where we have a temperature change as a result of adding heat, and then there's one where work moves the piston a certain amount. So basically what we want to do is understand in phase 1 and phase 2 which energy balance terms we have and which we don't. So if we look at phase number 1, we know we have no potential energy. We know that's something that the problem says that we can assume. And then the piston is never accelerating in this problem. And because it's never accelerating, we're not going to have a change in kinetic energy, especially between these two. Obviously, your piston's not moving. And then there's no work that's done on the system here. There is something happening with regards to temperature, so there is probably a change in internal energy. If you look at phase 2, same thing here, no potential energy. There's no acceleration, so there's no kinetic. But there's also no change in internal energy because if you look from here to here, the problem says that the temperature does not change. So if the temperature doesn't change, we don't have a change in internal energy. So let's take that information and let's solve this problem. So for phase 1, we write our closed system energy balance. Your heat plus your work equals the change in internal energy plus the change in potential energy plus the change in kinetic energy. So if we look at all these terms that we could cancel, we can cancel out our W, we can cancel out our E sub P and our E sub K. That's going to leave us with the amount of heat that enters the system is going to equal the change in internal energy. So we can very simply say that delta U is going to equal Q, and we're going to just want to do some unit conversions to make sure that we're in some good, easy units to use. We generally want to see some joules in this class to make it a little bit easier for ourselves. So 1 kilocalorie is equal to 1,000 calories, and 1 joule is equal to 0.39 calories. This is a good unit conversion to maybe have on a cheat sheet for an exam. And that means that the change in internal energy is going to be 8,370 joules. So that's phase 1. Very, very simple. It's just getting us to practice how do we cancel out these terms and find what we need to know. Let's look at phase 2. In phase two, we write our general balance equation again. This is our new one for closed systems. And if we look at what we only have work and heat in this system. So that means your heat is going to equal to your negative work, but work was defined as negative above, which means that your heat transferred is going to be 100 joules in this scenario. So that's it to this example. It's a straightforward idea of how do we basically take these balance equations and make them easier. So one thing that I do recommend as we start to go forward with these problems is that you draw yourself a picture so that you really understand what's going on in the words. Translating those words to the picture is kind of always the hardest part in these types of questions. So make sure that you understand why we cancel out these terms and that you've got these answers written down in your notes.